Now, before doing another example, actually, what I want to do is I want to show you a connection between this equation that we've created and the connection between equations and graphs that we were looking at with previous examples, right? You might remember this video from before. So is there a connection between what we've just created in graphs? Absolutely. So let's look at this equation. S equals 2f minus 1. And if you like, instead of looking at it like s equals 2f minus 1, we can look at it with more familiar variables, if you want, y and x instead of s and f. But in any case, we can look at ordered pair solutions that we were able to achieve. So we got some ordered pair solutions here, actually. So let's keep track of those. So if we have an f and s table of values, when we have figure number 1, we only had 1 square. When we have figure number 2, we had 3 squares. When we have figure number 3, we had 5 squares, and so on. And we could just keep going like this, right? We could even go up to 89. For figure number 89, we actually have 177 squares, and it could continue beyond that. We could predict how many squares must be in figure number 200 million if we wanted. So here you could look at this table of values, and each of these corresponding values you could actually interpret or write as ordered pair solutions. So here, 1 and 1 is an ordered pair solution to this particular equation. 2 and 3 is an ordered pair solution. When f equals 2, s must be equal to 3. 3 and 5 is an ordered pair solution. 4 and 7, and so on, right? And we have many more ordered pair solutions here. Now, if we wanted to graph this relation, then we could do that. So we could graph this relation by taking a horizontal axis, and we don't have to call it an x-axis, actually. This horizontal axis we could also call the f-axis for figure. So that's where our figure number goes. And we could write this y-axis, this vertical axis here, but we don't have to call it the y-axis. In this case, instead of the variable y, we're using the variable s. And so we could say here this represents the number of squares. And so if we have the number of squares on our y, or we could call it our s-axis, and the figure number on our f, or we could call it our x-axis or horizontal axis, it doesn't really matter. Anybody would understand what you mean if you called this by accident the x-axis. We could then plot these ordered pairs, right? So 1, 2, 3, 4. We only go up to 4 here, but we could go up to 5 if we wanted. And so how many squares would we need? 1, 2, 3, 4, 5, 6, 7. So this is the 1, 2, 3, 4, 5. It's good to write, at some point, it's good to write how far you're going up with this scale, because it could be that each tick mark actually represents some number other than 1. So instead of counting up by 1s, you could count up by 5s, like 5, 10, 15, 20, 25. So if you were going up by 5s, you would say this part in the scale represents 25, but we're just going to count up by 1s. So it is important to label what's called your scale, the scale of each axis. Now, your solution of 1 and 1 you can plot here. Your solution of 2 and 3 you can plot here. Your solution of 3 and 5 you can plot here. Your solution of 4 and 7 you can plot here. So 4 and 7. So these are all of your points, 1 and 1, 2 and 3, 3 and 5, 4 and 7. Now, a question you could ask here is, should I connect all of these points into this nice line like I've done with my previous examples, right? Can I be justified in doing that? And the answer is no. The answer is no in this particular case. And the reason for that is because this particular equation, it models the relationship, particularly between the figure number and the number of squares that exist there. And if you wanted, you could plug in a number in between what we've plugged in. So you could try plugging in 1.5, right? And you would have s equals 2 times 1.5 minus 1, which would be 3 minus 1, which would be 2. And you could argue, okay, the point 1.5 and 2, it should be on this graph, right? The point 1.5 and 2, it should be right here. But no, it shouldn't. And the reason for that is because this relation carries meaning. And we can't define a meaning of figure number 1.5, right? We are listing our figure numbers by whole numbers here. Figure 1, figure 2, figure 3, figure 4. There is no figure that is defined in between them. So because of that, we say we can only plug whole or natural numbers, let's say. We can only plug natural numbers in for f. And so because we can only plug in natural numbers in for f, we can't plug 1.5 in here. It doesn't make sense for the situation that our relation is modeling. And so we can't really justify filling in all of these points here. So what we do is we just leave it. We would just leave this as what we call, discrete points. Discrete means that they're not connected continuously in this line. So here, this would be the graph of that particular relation. And keep in mind, if the relation carries some kind of actual meaning, for example, here we can't really define what it would mean to have figure 1.5. We can't define what it would mean to have figure pi, right? 3.14159 forever. What figure? How would we determine? It just doesn't make sense. So here we would say we can only plug in natural numbers, and because we can only plug in natural numbers, we can't define corresponding solutions for f values in between these natural numbers. And this would be our graph. And in the next video, we will, I promise, try another example.